Good afternoon, everyone. Good afternoon, good morning, good evening to those joining online. Today we will talk about inference at record speed on our Azure ND series of virtual machines. So one thing that might have drawn you here is the big announcements of the almost 900,000 and 1.1 million tokens per second that we reached on our ND GB200 and GB300 series. So we will walk you through that today. My name is Hugo Affaticati. I am a senior cloud infrastructure engineer at Microsoft Azure. I've been working on performance validation and benchmarking for the past 5 years, and I'll be joined on stage by my colleague Nitin Nagarkatte, who is our AI product management lead for the ND series on Azure. A little bit about the session today. So I will be talking about inference, optimization, how we reach those big milestones for the first half of the session, and then Nitin will be talking more deeply about the infrastructure and the product roadmap for ND series. So as some of you might have seen back 6 months ago at Build, we announced, and by we I mean our CEO Satya Nadella announced 865,000 tokens per second on one full rack of the ND GB200 V6 virtual machines on Azure. So that is 18 virtual machines, 72 GPUs. Then in September, we unveiled in our official blog post the existence of our new AI super factory, Fairwater, with the two first sites in Wisconsin and in Georgia that are GB200 and GB300 powered data centers, part of a huge network of data centers of over 400 of them across 70 regions. Numbers that you probably have heard in the keynote and in multiple sessions already in this conference. Our goal today is to give you clear insights and action items into the performance and the improvements that we do on Azure. As you are maybe software engineers, decision influencers, or decision makers in your company, you want to understand why Microsoft Azure offers the best performance and really understands every single item of a supercomputer to deliver top performance for your inference workloads. So throughout the session, you will see those QR codes. If there is a specific topic that interests you, there is a link to more resources to double-click on the performance. So 865,000 tokens per second. That sounds like a huge milestone. Let's hear a little bit from our CTO of Azure, Mark Russinovich, on what really the milestone is and what it means.
As part of our ML-Perf benchmark test, we use the industry standard LLAMA 270B model. It's an older model, but its size makes it the industry standard for hardware benchmarking and testing. And we ran Inference on Azure's ND GB200 V6 virtual machines, accelerated by the NVIDIA GB200 Blackwell GPUs, where we used a single full NVIDIA GB200 Blackwell GPU rack. One rack contains 18 GPU servers with 4 GPUs per node, totaling 72 GPUs. We loaded the LLAMA 270B model on these 18 GPU servers with one model instance on each server. This is the Python script we ran on each server. And using Slurm on CycleCloud, which is an inference framework, we ran them in parallel. You can see on this Grafana dashboard the tokens per second performance of model inference. As you can see in benchmark results at the bottom, we hit an average of around 48,000 tokens per second on each node. And above that, you can see that we're totaling 865,000 tokens per second for the entire rack, which is a new record. The bar charts on the top right show how consistent the performance is across the system, with very low deviation.
So how does this performance then translate to the everyday AI and agentic solutions that people right now are building on Azure?
So I don't have the exact numbers for tokens consumed per interaction, but we can use simple math and make a few assumptions to roughly translate this to everyday performance. For example, something easy like this prompt where I asked Llama about sysinternals consumes around 20 tokens. Under the covers, we need to add roughly 100 tokens for the system prompt and an extra 500 tokens as a proxy for what's required to process the prompt. Then finally, the generator response is around 1,400 tokens. So the grand total is close to 2,000 equivalent tokens for this one interaction. Remember, our benchmark test showed 865,000 tokens per second. So let's divide that by the 2,000 tokens in my example. And that translates to around 432 user interactions per second per rack in Azure, Or if you extrapolate that over a day and estimate 10 interactions per user, which is pretty high, that's around 3.7 million daily active users. And by the way, everyone should already know how to use the system internals tools and not need to ask that question.
So 3.5 million user interactions. That was our milestone 6 months ago. Today, as we announced the general availability of our ND GB200 virtual machines powered by the NVIDIA GB300 Blackwell GPUs, we reached 1.1 million tokens per second. This is the new milestone here at Microsoft, which means 27% more performance over the previous milestones of the GB200 performance. That is approximately 4.5 million interactions per rack. As we were mentioning, as you probably heard, our data centers have hundreds of thousands of GPUs, which means dozens of thousands of racks, which means almost 100 million user utilizations per day. Our baseline was the H100, as you probably are familiar with, the H100 GPU from NVIDIA. There were 8 GPUs on each virtual machine, and then we put 4 virtual machines per rack. So that means a total of 32 GPUs. If you compare to Blackwell, 72 GPUs, it's more than double, which means how dense the racks really are. And as you can see at the bottom here, the performance on one virtual machine used to be 24,000 GPUs. We are now at 1.1 million, as we mentioned. So let's understand the performance. Let's start with the building block of performance, which is one GPU. Here on the presentation, you can see the baseline of H100 at approximately 14 or 1500 T-flops of GEMM performance. GEMM is really the building block. It's the matrix multiplication, which means how many multiplication can happen during your model per second. On the GB200 and the GB300, it's 2 to 3 times more, depending on whether you look at constant or randomization. The difference between the two is very simple. Think of constant initialization as the peak performance that one can achieve, and randomization as the performance that is actually representative of your model and your inference on the model. How do we reach such high improvements? The first key item is the memory of the GPU. The memory on a GB200 being 192 and on a GB300 be 288 gigabytes. It's 3 to 4 times more than the baseline of H100. The second thing that is really important is the bandwidth. Because high memory requires also high movements of data in and out of the GPU, a bandwidth that is 3 times faster removes the bottleneck that is usually connected to GPU memory. The next thing that is very important to know is how we put them together. So the baseline again, 8 GPUs divided in 2 sockets. All the GPU talk through a PCIe switch that is connected to the CPUs, and then there is the NV switch to connect GPU together. That performance gives 50 gigabytes of performance from the CPU to the GPU and the GPU to the CPU, or around 700 gigabytes of performance from GPU to GPU. That was the baseline. As you've heard in the past, we partner with our partners NVIDIA, AMD, and others to build the next generation. And I'm here presenting you the latest, which is how a GB200 or a GB300 NVL domain, an NVLink domain works. It is 2 sets of GPUs connected to the graced CPUs, and that would represent what we call an NVL4, if you've heard that term before. The performance of such technology, which is the NVLink C2C, chip-to-chip, is 4 times higher bandwidth on the host to the device and the device to the host, and 3 times higher on the device to device. It is also a much better energy efficiency, which means that we can focus the energy use into the GPU and a lot less into the communication between the host and the device. Having those virtual machines together, you need to scale up. one virtual machine is no longer the base for inference. We see much bigger models with agentic AI having multimodal models, things like that, that require a tremendous amount of GPUs. So what really becomes the next bottleneck for most would be the network. Here on Azure, we make investments into two key versions of InfiniBand that would be the CH7 and the CH8, offering 400 gigabytes of performance per NIC. There is a huge difference in how many NICs you have and how many network systems you have. By that I mean that if you have 400 gigabytes over one NIC, it is very different than 100 gigabytes 4 times over 4 NICs. That creates overhead and that creates bottleneck in your workload. At Microsoft, we measure this, and that's why we've decided to go with the CH7 and the CH8. The next really important part of understanding your workload is how to scale. We have been talking from the beginning about smaller models, like the example of the llama 70B model. Here, I'm sharing with you an example on our bigger model, and that would be the Grok 314 billion parameter model. This big model, we train on H100 from 1 to thousands of GPUs to understand really the scalability for both training and inference. In this session, we're focusing on inference. But what really is important to know is how even on H100, which for some people thought it was obsolete, it actually is the opposite. We do see the scaling that is required for such big models and the next level of agentic AI. As you can see here, from 32 to 1,000 GPUs, the scaling efficiency is around 95%. And then from 1,000 to 10,000, the scaling efficiency is around 97%. This is really key for the next generation of workloads that you're building and that you will be inferencing on Azure. And it is due to the great quality of the image that we do. At Azure, we spend the time to look into the NICOR library and to build it into the image to ensure that the correct topology is being used. I'm sharing here 6 examples of experts for NICOR performance improvements that are true to H100. And then if you were to follow that QR code that I'm sharing, there is also the ones that are associated with GB200 and GB300. As I mentioned, everything is built into the NICOR library, into the image on your virtual machines. That means that you have performance out of the box. Some optimization that you need to be aware of as well. Many people think of inference equals batch size. For people who are focusing on throughput, this is true. Things that are also very relevant in the era of inferencing and people using and interacting with the model more and more is the time to first token, for example. It would be the latency. If you take those two very important equations into mind, it would be, you know the size of your memory, you know how much memory you're using for your processor, for your hypervisor, for your image. So let's say the example of the 288 gigabytes of memory of the GB300. Let's count large, let's count 10 gigabytes for the host. Then you take your model. So that means that you have 278 gigabytes available. If you take a small model like a llama 3.8b, which is the new industry standard for startups, for example, it is 8 gigabytes precision of PF8 means that you're using 8 gigabytes for your weights on your model. You're still left with 270 gigabytes of memory on your GPUs. And then there is the KV cache. The equation here really explains to you how to find the correct version of batch size, which means throughput versus latency. And then you would reach one of those curves that we're sharing here about what matters the most to you and where your optimum is for your model. This is the type of work that we do for the model that we run on Azure. If you were to go a little bit higher in the abstraction on the stack, if you're just renting tokens really out of Azure, or if you're looking into the performance, that's the type of work that we do when we partner with our partners for developing the next generation of GPUs. Moving back to the original work that we have done and that we've shared the 1.1 milestone, This is here recapitulating all the work that, summarizing all the work that we put in sharing the precision size, sharing the optimization that we've done, sharing the nickel test, how it scaled. And what you can see is that on the 18 machines that we have, we run from, on average, 61,000 tokens per machine, aggregated to 1.1 million tokens per second, and a variation of less than 5%. It means that all those out-of-the-box performance are a security to have on Azure. And then one more level of approval on this is that we partnered with a third-party Signal65 to confirm the throughput and the latency that we've seen on Azure. So that was for the small model and how we optimize them. And then now I will invite my colleague Nitin on stage to talk a little bit more about the roadmap and the infrastructure. Thank you.
Hi, everyone. Good afternoon. My name is Nitin Nagarkatte, and I'm a AI product manager at Azure. And thanks to Hugo for walking us through a lot of the details of what really goes on behind the scenes to optimize performance and to extract the most amount of value you can from the GPU infrastructure. The rest of the talk, I'm going to be talking a little bit more about some of the building blocks of our infrastructure and how we at Azure are building all of this out for you folks to actually use in your various use cases. Before we go into all of that, let's just take a step back. And I think all of you are familiar with this already, but I'm just going to put it here for kind of context and just to show how crazy our world is. So this is a plot just showing model size growth over time. All of this AI stuff that we're talking about really started around this 2019 timeframe when GPT came out. Just a reminder to everyone, this was all done on Azure infrastructure, which was a pivotal moment in terms of all of the AI industry that we're seeing evolving today. And from the 2021 ChatGPT moment, really, it kind of kickstarted all of these various use cases that are being built using AI capabilities. Even 21, 22, most of it was still text-based, assistants where you could basically talk back and forth with some of these AI machines, but nothing meaningful in terms of actual workflows being driven here. The model sizes at this time were roughly 175 billion parameters for the GPT model, and then just continue to grow from there. So in 2023, which is when the industry kind of really caught up, we looked at GPT-4 coming out, cloud models coming out from Anthropic, and various other models, including llama, becoming more mainstream. This is when we started seeing models in the hundreds of billions of parameters of size. And again, the reason I'm calling this out is because of some of the math that Hugo was talking us through. Each parameter needs a certain amount of memory to be stored in the compute environment. And if you have hundreds of billions of parameters, then you also need corresponding amount of storage available very close to the compute environment. So that's really what drives a lot of the complexity in the underlying infrastructure that's needed. Last year, it was all about multimodal, long context models. We saw a slew of models come out, and these were roughly in the 1 trillion parameter range. And from there, all of this year has been about agentic workflows, right? Everywhere you go, we're talking about agents. We're talking about how we can automate various kind of workflows and make it much more hands-off and much more capable in terms of things that we can achieve using AI capabilities. The state-of-the-art models today are in the trillions of parameters, which means, again, just going in the last 5-6 years, the size of the parameters has just kind of been going parabolic, right? What that means is we need a corresponding infrastructure to actually support all of this. Again, I'm going to remind everyone, we started this journey with that first GPT model on Azure, and we've been constantly building out the next generation of compute to really power every step of the way over here. So let's take a look at what are some of the key layers that enable this technology and this revolution. At the very base over here is the core infrastructure layer, really kind of the hardware and the bare bones of what really goes in here. This is the compute, so it could be CPUs and a large amount of GPUs typically. Interconnect, which needs to be fast, which needs to be scalable, and of course storage. As I mentioned, you really need to store a large amount of data to train these large models, plus the computer itself needs to be able to store the large models in memory. On top of this sits our Azure AI platform capabilities. So think about this as a collection of various technologies around virtualization, allocators, schedulers, Kubernetes, if you use that, combined with standard frameworks like PyTorch that really enable developers to take this underlying infrastructure and do useful work, train models, run inference on them, and really get outputs out of them. Azure also provides a large number of managed AI services for people who don't necessarily want to be running at that lower level of infrastructure. If you've seen some of our keynotes and other talks, Azure Foundry now supports, I think, something like 10 or 11,000 models. I forget what the number is. It grows every day. Azure AI Studio enables a workspace or a playground for people to dabble with various models, create various use cases. I'm sure you've been to some sessions where they went through details about how you can use Azure AI Studio to actually build out for your own use cases. And at the top of all of this sit the customer experiences that you're really trying to build out. So these could be Copilot-based experiences, custom agents that you want to develop to solve particular business problems, pretty much anything you want to do at this point. We're going to focus a little bit more on that bottom layer, the AI infrastructure layer, starting with our GPU portfolio. Our flagship series here is the ND series of GPU machines. These are the state-of-the-art machines that we worked very closely with our partners like NVIDIA and AMD to develop. Starting with A100 series of GPUs a few years ago, we've been building out several generations, pretty much one every year. And currently, just yesterday, we announced general availability for our GB300 series, which is at the bottom right there. We've also worked with AMD to develop machines based on their GPUs, and we're continuing to partner across the industry for this. But not all models really need these massive machines, right? The massive machines are really useful for 100 billion plus parameters to trillions of parameter kind of models. But if you look at a lot of models, they are in like the smaller, medium to small range. And for those, you can actually use a series of different compute capabilities that are available. So our NC series really solves for that much more efficiently. We have some of our NC series that has capabilities of going up to a couple of GPUs that are interconnected for medium-sized models, whereas for the really small models, you can actually use slices of GPUs that makes it much more cost-efficient. Just yesterday, we also announced our NC-V6, which is the middle box over there, which is based on NVIDIA RTX 6000 Pro GPUs, which is now in preview as of yesterday. So we've been busy. We've been trying to develop the latest and greatest technology that can support the AI revolution that's unfolding around us. Digging a little bit deeper into the NC-V6, this is basically our first converged platform where we are essentially combining compute-intensive workloads, basically the inference workloads, with our visualization platform. The way this is done is by combining the RTX 6000 Pro GPU from NVIDIA with Intel Granite Rapids CPUs. And these have native support for MIG, which basically means you can actually scale from slices of the GPUs for particular workloads to multiple GPUs for larger workloads. So you don't need different types of machines or infrastructure to do this. I won't go into the details of the table below, but basically what this shows is different configurations you can achieve on the NC-V6 for different workloads, whether it's inference, whether it's things like remote desktop, or whether it's graphics-intensive workloads. Let's spend a little bit of time looking at our ND series, which is, again, our flagship series for large model training and inference. The basic building block over here is a super chip, which is basically combining one Grace CPU, which is an ARM-based CPU, with two Blackwell GPUs. Multiple generations over there, B200, B300, with varying capabilities. These are combined together, so two of these super chips combined together in a single tray to create a sled or a compute tray. And we combine Azure technologies like Azure Boost, which basically enable connecting this tray out to the outside world to form our fundamental building block for our virtual machine. So one virtual machine in the ND series is really this tray in the hardware world. We slot 18 of these together in a single tray. So think about this as a big cabinet, 18 of these slotted together and connected together by the NVLink, which is a high bandwidth network, 1.8 terabytes per second. And basically what this NVLink does is it creates a sort of a converged memory space for the entire rack. So effectively, when you're trying to train or run inference on models, what you're seeing is all of the memory pulled together across the rack, right? So the GPUs across the rack can access memory anywhere in the rack at very high bandwidth, and that immediately translates into high performance and capabilities that were just not possible just 1 year ago. These racks are then put together in large data centers, connected together with InfiniBand technology, essentially scaling out to hundreds of thousands of GPUs as needed. The InfiniBand technology as well over here is built out in a very particular format, so we are highly optimized to ensure that we are delivering the maximum performance possible. And the configuration that we are really using over here is a non-blocking fat tree. So effectively, every GPU can talk to every GPU at line rate. This is really important because when you're trying to train large models or even run inference across multiple GPUs, you do not want your GPUs waiting for data. You want them to be constantly humming away, churning away data. So having a highly effective interconnect is critical. Just a couple of years ago, there were studies that showed that GPUs were just sitting idle, waiting up to 50–60% of the time because they didn't have data to crunch. And having a highly optimized backend network really solves that. Our network is also capable of full. It's built out with full nickel integration, supports MPI, lots of fancy features like hardware offloading, intelligent routing, and so forth. And all of this really results in just 1.5 microsecond latencies when you're looking at data passage between GPUs. So this is all critical to ensure that when you are interacting with an AI agent, for example, and it's a real live session, you're not waiting for a response as much because of this. So the network is ensuring that data is flowing as fast as possible, as fast as electricity and physics allows it, to ensure that you have a good customer experience. Finally, touching a little bit upon storage. So there's typically 3 pillars that enable all of this. There's compute, which we spoke about. There's network, which we already spoke about. And let's touch a little bit upon storage as well. For any fast compute, we need to have fast storage because essentially we need data to crunch through. And this is especially true for inference because you're trying to do real life interactions with customers and enable the good experiences over there. So if you're looking at types of data that are typically used in these AI infrastructure, there's 2 broad categories of data. One is enterprise data that is feeding into all of the compute, and the other is the model themselves, the model artifacts themselves. What we've done at Azure is build out hyper-optimized capabilities to support these specific kinds of data so that we're able to deliver the highest performance possible at the best cost possible to our customers. So the first one here is Premium Blob, which is basically blob storage, which you all might be familiar with, which is built on top of SSDs to ensure that we're able to deliver object storage at extremely low latencies, and not just low latencies, extremely high consistency with the workload. So the plot on the right side actually shows how much of an improvement we see using Premium Blob. On average, we see about a 10 times lower latencies using Premium Blob. And if you look at 99th percentile, that's almost a 40x improvement over just standard block storage, standard object storage. So this is again critical in terms of delivering a smooth customer experience and accessing the right amount of data. The second innovation that we've done here is the Azure Container Storage for models. This is basically making use of our block storage capability, but also spreading it across the NVMe that's actually present on the physical racks that I showed earlier. By doing that, what we're able to do is really deliver extremely low latency for these models. We never really want our compute waiting for models to load up, right? We want the models to be loaded immediately. We want to be humming right away. We want to be crunching numbers right away. And that's enabled by this technology, which basically ensures that we are about 6 times faster than where we were before this existed. So we continue to innovate in every space, whether it's compute, whether it's storage, whether it's network, to ensure that we're able to deliver the highest levels of performance, enable the latest capabilities, while controlling costs for all of you. So we spoke about all of these building blocks. How does this actually come about in terms of global deployment? Azure actually has over 70 regions worldwide today, and we have over 200 data centers, and we're continuing to build constantly. What this translates to is hundreds of thousands of miles of fiber that's being laid out, and various capabilities that we continue to innovate on to ensure that our customers, wherever they are in the world, can access the right kind of technologies. Another example is the AI WAN that we've built to ensure that AI regions are connected together with the highest bandwidth possible. I'm going to take a step back and let this video speak for itself.
AI is creating a future where everyone will need access to it. And for every promise being made about that future, there's just as much talk about who's going to get us there. At Microsoft, we're doing a lot more than talking. We've been building. Not just a data center, but a global network of AI factories designed specifically for the age of AI. By taking the lead in developing intelligently networked infrastructure, Microsoft has scaled the world's most powerful AI data centers into an exascale supercomputer, building purpose into every last detail and delivering the level of performance that AI applications are going to demand. We're putting in the work to do it responsibly, and we're not doing it alone. We've partnered with NVIDIA to connect these AI factories to hundreds of thousands of the latest Blackwell GPUs, accelerating global performance to redefine what's possible. Because anyone can dream up a future in AI, but it takes scale, time, and investment to turn a dream into reality. So to the enterprising architects of our shared AI future, we built you a foundation so you can build what's next.
And that's it for our talk here. Just to summarize, we have our latest ND series in GA now, our NC series in preview for large scale of models. We also have a session on our supercomputing infrastructure coming up on Friday, if you're interested to learn a little bit more about what we do behind the scenes to enable the leading frontier model training that's happening on Azure infrastructure these days. And finally, we have a lot of our experts at the expo just across the street here. Feel free to stop by, ask us questions. We are more than happy to engage. Thank you.